Well, Joseph, how are you? Congratulations on winning the game. I sent you the gift card for quizzes. Okay, we're gonna work on Unit 12 this week. So check out your notes and your assignments. And I'll start in about a minute. You're welcome. Okay, so download your notes and your assignment. We'll get started shortly. Hello, Jarrell. All right, we're gonna go ahead and get started. So a little longer today as far as the notes because we're trying to meet all the objectives in the course. And this week we're gonna go back and talk about GIL, and we're gonna talk about handling and coordinating threads as they share resources. And we want to talk about different types of issues that you might come across as developer, such as deadlocks, starvations, and race condition, and how we can prevent that by using some of the tools that we have in Python. All right, so this week we are going to cover chapter 19 through 21. We are going to touch a little bit on how to be able to manage these, and then talk a little bit about the pattern down the line. So in the first part, it touches on what deadlock is, and I think we mentioned a little bit of this before. This is a very common problem, especially when you're working with threads. So when you're working with your project, and if you're using threads, you want to make sure that you coordinate your threads, as we mentioned before. But most importantly, we want to make sure that we implement lock objects. It is okay for us to put in threads, but it is better that we have the lock object. And we started seeing this last week. So deadlock is a situation in concurrent programming that you cannot have progress because a resource has been locked in the current state. So it could be that you have one thread that is utilizing the resource that you have, and it won't release it for other threads to continue. So in that case, what you have is your program doesn't really have much of any kind of outcome. It will just hang. And we don't want that, right? We don't want major delay, because the whole point in concurrent programming is to be effective, efficient, and drive performance. So here it talks about an example where you have philosophers sitting around the table to eat. And if we coordinate how they eat, right, it will be better as far as the outcome. So the first bullet says that for each philosopher, we can think about how if they all pick up the left fork that's available, or until they pick up the right fork that is available, when is that, right? Or if they're picking up both forks, okay? And so if the process continue as we go from the left to the right to both forks, if they are picking up all the forks at the same time at the beginning, meaning that if we replace the fork with resources, if all the threads is utilizing that same resource, then are we going to be able to have progress? So now, if the threads are not able to release the resource, then we're not going to be able to proceed, as you see in the example. So in a deadlock, all elements of the system are stuck in the same place, and you won't have progress in your program. When you're using multiple threads and processes, if the process is waiting or the thread is waiting for another one to release the resource and prevent other processes from execution and update the state, then we are going to have a deadlock. Now, for deadlocks, by the conditions of the concurrent program that needs to have the same time of the deadlock occur is called the Coffman condition. So Coffman conditions is when you have deadlock that occurs in the concurrent program. And so we would have some conditions that are stated here. Mutual exclusion. At least one resource must be a non-shareable state. So you would be dedicating that resource for a specific thread or process. And because this resource is going to be held by that thread of the process and not be utilized by the other. So you are going to exclude that particular resource. And so if we think about shared resource, this is not achievable. So when you plan out your program of using multi-thread and multi-process as you are required for your project, we want to think about how we can dedicate a container or storage location that is non-shareable for a particular reason, for a particular thread and process. The second condition is hold and wait. That means that one process is going to be accessing the resource and it's going to be waiting for another resource to be available after another thread is releasing it. So what it is it's still using the current resource, and while it's waiting for another resource that is available after it's being released. The third condition is a non or no preemptive condition. This is only being released, the resource is only being released by the process voluntarily. And so once the thread is done or the process is done, then it's going to give up that resource for the other. And so the resources, while it's being used, is going to become non-shareable. So that means that other threads are still going to wait for it. So in the non-preemptive condition, the resource is only being released based on when the thread is complete or when you create for the thread to release. So we have to think about these conditions as part of the Coffman conditions when we're dealing with deadlocks. Now, for circular wait, if the first process is waiting for the resource to be released by the second, for example, A is waiting for resource 2, and resource 2 is being used for B. B is waiting for resource 1, which is being used for A. So in this case, both of the process or the thread is waiting for the resources that's held by the other. So it becomes a non-ending waiting game. So you would have a circular wait. Now, when we look at the example in Python, you would see something like this. Okay. So in this one, we're using multi-threads, and we would import in threading. We would have the time for the delay. So in the first function, you have thread A, and we want to print thread A is starting, and we're going to print thread A is waiting to acquire lock A. Here we would have a lock. So to lock the condition, to lock in the resource for A, you would create a lock object. Then thread A is going to acquire lock A and it's going to compute. So we want it to slice the time. So we are going to implement the delay for 2 seconds. And this allows multi-thread to concurrently perform, yet so while this is waiting, thread B is going to be activated and then lock and so on. So once you have the time sleep implemented, you are then going to lock B. So thread A is going to wait to acquire lock B. So we're going to lock for B here. We're going to print thread A is acquired lock B, and it's going to perform some calculation. And so as lock B is part of the thread A functions, right, it's going to lock the resource. And then we're going to pause again for 2 seconds. Once it's done, then we want to release. And you simply use, right, the lock and then with the release method. So we would release lock A and lock B. After that, you have the function called thread B. And similarly, you are going to start thread B. We're going to print thread B is waiting for the lock. And then we're going to lock for the thread B. So it's going to acquire first. So once it acquired the lock, we're going to have it wait. So we're going to put it to sleep. Then we're going to lock using lock A. So it's going to acquire lock A. And then it's going to perform calculation. Then it's going to wait 5 seconds. After that's done, it's going to be released. Now, as we are creating and using the lock object, here is when we instantiate the object. So for lock A, you simply create a lock object called threading. And so you implemented the lock method from the threading module, and we're going to call that lock A. And we do the same thing for lock B. So after you defined it, you then can implement it in the function like this. Then after that, we would create your threads. So we have 2 threads in this program. We're going to start them and we're going to join them. And you can do them separately, but as you have more than 2, then you want to loop. And then we would finish. So in this program, what will happen is as you implemented the lock, you can prevent, right, the deadlock condition from happening. So when you run this, you would see simply we start, right, we acquire, then it's going to lock for A, perform calculation. So while it's doing that, thread B is going to lock for B. Okay. So as we want this to be concurrent for thread A, once thread A acquired the lock and perform calculation, as it goes to sleep for 2 seconds, during that time, thread B is going to lock B. So it's going to start here for this function. Then thread A is going to wait to acquire lock B, and then thread B is going to wait to acquire lock A. So at this point, what you see is it's never going to finish because now we have a circular wait, right? It's not going to be released, as even if we put that to be released here, that each one is going to wait for the other to release the lock. Okay. And then, so it would never reach this part right here as far as finish. So in this case, right, your program will not complete. So if I need to end my program, I have to click stop. Okay, so it won't ever reach this last part here. So this is an example that you would see for the circular wait. So to answer our questions for the assignment, for number 1, it says, when does a deadlock occur in the concurrent program? How do you resolve a deadlock? And we can say that the deadlock occurs in a concurrent program when all program elements require the same resources to complete the task at the same time. And as the resources are not released from various elements, no task is achieved, and no progress is made in the program. So you would have a program that will infinitely hang. To resolve the problem, we would establish links between the locks and the resources. Okay. We have to think about how we coordinate the lock of the resources as well, because if we don't, you see that we might have a circular wait. Then we're going to control the order of the resource access across the processes and the threads. So establishing the lock is the initial step for our resources. But we also have to coordinate the order of how the resources are accessed by the threads and the processes. So logically, you have to think about your algorithm, right? The steps that it needs to take in order to proceed or complete the program. Then for number 2, we touch on these Coffman conditions of deadlocks, which are mutual exclusion, where the resource must be in a non-shareable state. The resource is held by that individual process or thread and cannot be accessed by others. Second condition is hold and wait, as one process is simultaneously accessing the resource and is waiting for the other resource that's held by the other thread. So even if you give it 2 seconds, sometimes if the thread or the process doesn't release it, it will continue to wait and as it would go on hold. Okay. Then you have a no preemptive condition. This is only when the thread or the process is voluntarily release the resources. And that means that as they don't release the resources are not shareable. And if you have a thread that never completes and it's using the majority of your resources, right? All the other threads will just be on hold. And so that first thread needs to release in order for the other threads to proceed. As we implemented join, that will be required that it has to wait for the completion of the prior thread to access the resource. Then you have the circular wait, which we see in the Python example. If the first process or thread is waiting for the resource that's held by the second, and the second is waiting for the resources that's held by the first, we have an infinite wait. So they both wait for the resource that's held by the other. And you can find this in the notes. Any question? So Coffman conditions, make sure we know this. It will likely come up on your final exam. I will do a final review later, right? You will see that in the upcoming weeks. So Coffman condition is on page 1 and page 2. Then your example, and if you want to run this, you can copy and paste it into your IDE so you can take a look at how the threads are written for circular wait. Okay, and this gives you the breakdown, right? A visual of how the procedure for this particular program. So as you look at this, your thread A and thread B, right, even though they start and they acquire the lock. So thread A acquire lock A, right, and thread B acquire lock B. And so when that happens, they each wait for each other to release the resource in order to access. So even if they try to acquire during that wait time, right, you have a deadlock program. So how do we fix this problem? And this is going to lead us into example 2. So in example 2, you have the same function, okay, where you have thread A acquire lock B, goes to sleep for 2 seconds. After it acquire lock A and go to sleep for 2 seconds, then it release. Then you have thread B. Thread B is going to acquire lock A, sleep for 5 seconds, acquire lock B, sleep for 5 seconds, release both locks. We instantiated the lock objects using lock method from threading module. We create the threads, and the target here is simply our function. And then we start join and finish. So when you run this, right, as it would wait, so you start A, got A lock, B starting, acquire lock B, lock A, thread B acquired lock A and perform. So while it waits for the B lock, and then it's going to acquire lock B because A release lock B, okay? And then thread A is going to acquire lock A, and it's going to wait for lock B. Thread A is going to acquire lock B and perform a calculation, and then it release both locks. So unlike the other program you have a circular wait or a deadlock. This program, what you see is that you have A started and it's waiting for the lock. So it goes to sleep while B starting, and B is gonna proceed, obtain the lock, the first lock, which is A, perform calculation, obtain the second, it waits for the block B, then it got the lock B, perform calculation. B will finish before A, so it's going to release both lock. Then A is going to come back and it's going to obtain A, perform calculation, obtain lock B, perform calculation, and release both lock. Okay. So coordinating how each of the function obtaining the lock is going to be important. So that way you don't end up with a deadlock program. Any question? Okay. So now you see the example 2 there. So if you want to run that, you can compare the program. And then for the example in the book, right, the example 3 is a way that they write it for the philosopher picking up the forks. Left fork first, right fork, and then print that they're eating. And so with that, you would create a group or your thread pool, and you're gonna lock it. Okay. So here's your thread pool. Here's the object where you create the lock for your threads, right? So we would use a for loop there. And then um, for the last part, it would just, we use a loop to make sure that we start your threads. And this is going to create locks, deadlocks. So with that, we would fix it. Okay. So example 4 is a way that you can resolve it. Um, when you look at the program, it's mostly very close, but I think for the top part here, that we are going to control and coordinate the lock. So here they instantiated the self lock, and then it's going to use the ID, which is the number, and it's going to sort it. Then the acquisition of the lock. So it's going to loop through and it's going to set up the lock for each of the thread. And then it's going to release in reverse. So so that way you're not locking and releasing individual ones at the same time, because what happened is you have to work inside out with the inner loop, so you don't create the issue of double locking from one thread to another. Okay. All right. Any questions? Okay, so let's take a look at, let me see, the next example. We already talked about the philosopher one. So let's take a look at example four. This is example 4 for the fork. So let's do 5 or 8. I'll come back to this one. Okay. So on the next example here, you can set up a ranking of your locks, and this is going to help you with the speed. So here you see that they use the timer to measure the performance, but you have thread A, right? Similar to the first example that you see, it's going to print that it's starting, it's waiting to acquire the lock. So we're going to give it lock A. And then once that happens, we're going to print that it acquired the lock and it's computing. Make it sleep for 2 seconds. Then we're going to wait for lock B. So that means that we would acquire lock B, print that it got lock B and it's performing computation, sleep for 2 seconds. And then we're going to have A release both locks. For B, here we are going to start thread B, just like before. We're waiting to acquire lock A. We got lock A, perform calculation, sleep for 5 seconds. B is going to also acquire lock B after that, and it's going to compute, sleep for 5 seconds. Then it's going to release both locks. We are setting up the locks A and B, and then the threads A and B. We're going to start the clock, and we're going to start the thread. We're going to join them, right? and then it's gonna give you the printout. Okay, so let me copy this and so I can run it for you because I don't think I have it in my IDE. Okay, so when we take a look at this program, right, you see, as expected, very similar to the first example and the second example that you see. Um, you start your lock, you acquire, or you start your thread, you acquire the lock, and it performs. So A got lock A and it performs. Then B is waiting for lock A, and A is waiting for lock B. And so thread A is going to acquire lock B. It's going to release both locks. So B is then also going to pick up lock A and perform computation, wait for lock B, obtain lock B, and perform computation and then release both locks. So unlike the second example, this one is coordinated where you rank the lock. So instead of B completing the task first with using A and B, while A is waiting for the locks, we have A completing it with the lock A. And then we start thread B, wait for lock A. So A is going to release the lock A, and then it's going to wait for lock B and release lock B. So once it releases both, lock B is going to be able to complete. So this gives us 14 seconds for these two threads. Okay. So you can check out the example there. So when you think about your program for your project, think about how you would implement threads or process, and then using lock to prevent deadlocks like that. But you need to coordinate. Okay. And this example below here is going to be a little longer, as it would be comparable to if you don't run it as a concurrent program, even though you set it up this way. Okay. So we can run this so you can see. Sorry, as we get closer to the course, your program is a tiny bit longer. So I'm going to clear this. So when we look at this example now, right, you still have the same function. It's going to acquire the lock. The first is going to be lock A. It's going to compute, sleep for 2 seconds, acquire lock B, compute with lock B, sleep for 2 seconds, release both locks. So pretty much the same as before. We created the lock objects, the threads, start the clock. Now, a little different than the last program that you saw. We're going to start thread 1. We're going to join thread 1. We're going to start thread 2. We're going to join thread 2. And then it's going to finish. Okay, so that means that A is going to run first, and it's going to complete first with both locks. Then B is going to wait, and then it's going to run. It's going to obtain both locks and then finish. So in comparison, you're going to get like a pretty close, tiny bit longer, right? So approximately about the same time, I think 14 seconds. But in this program, the coordination is that the first thread, thread A, is going to complete its entire task with both of the lock before B, right? So B is going to obtain the lock A after A releases it, and then it's going to wait for lock B and obtain lock B. So this is more of a sequential flow as you start and join, right? for the first and then the second, compared to here where you start both and join both. So it makes a slight difference, right? So when I run this before, you saw that it's about a tiny bit longer for the second program. Same. So in the text, like when they tested this, right, they felt that this is gonna be quicker, but when we test this now, when we run it, it's for on my system, it's roughly the same. But you get the idea that the first program here, we start both and then we join both, where the second program, we start, then join the first, start, then join the second. So it's more of a sequential. Okay. A first, complete everything, and then B, complete everything. Okay. So one important note, right? Each thread has to acquire the lock to complete the execution. Now, locks don't really lock anything. It's just a way that your computer flag the resources that's being accessed. So it would dedicate that resource to the current thread that's using it. And if it is poorly constructed, it tells you here that the threads or the process can attempt to access other resources without checking the lock first. So when you create the lock object, simply you create the flags for the resource for a specific thread. And locks are not always connected. So in the first question, when we answer that, we need to link the locks. And so now it tells you that it's not connected to the resources and do not block any kind of thread from accessing it. But when you use the lock in a dynamic concurrent data structure, you make sure that it is linking, and that's important, okay, between the locks. So you have to establish that link. So the resources are then being used by a specific resource, and it allows the synchronization of the resources from one resources to the next. Okay, so that's important to think about when you're using your lock object and coordinating your threads. Live lock, and for the next question, we can say that it is a situation where request of an exclusive lock is denied repeatedly. And when you have overlapping shared lock that's interfering with one another, you're going to have a live lock situation. So when we break that down, it really occurs when all the allow processes are setting up in a table. Then what you want is you want to make sure that your lock is non-exclusive. That means that it's not going to be overlapping with one another for the shared resources. And as you have overlapping lock, right, the resources are going to continue to not become non-shareable to the threads. Okay, so let's put that down for your answer for number 3. So to overcome the live lock, you need to coordinate the shared resources utilization and the lock request. So we want to make sure that we release it, right, before the next acquire is established. Okay, so you need to think about when the lock is being released for the next thread to acquire. because if you continue to lock it, then it's not gonna be shareable. Okay, so how does this interpret into Python? Let me double check. Yeah, so if you look at the next example, and you can run this as well. Okay. So in this example, we have threads, and you have the first class called spouse. I want to double check and make sure that we have the same one here. Yep, that's the same one. So with that, from the class definition, we have an init function. This is part of your threading module, so we would have to define the init for threading.thread. Then we're gonna instantiate your members. So this will be name, partner, and then hungry. We simply use a bool. So Boolean here for the value. Then the first member function after the init is going to be run. We have a loop. While self.hungry, we're going to print is hungry and want to eat. And we're going to plug in the name. And then we nest an if else and the with. So if the partner is hungry, right? Partner.hungry, then we're going to print whoever with the name, right, is waiting to eat. Else, we would have the with statement under the else with fork. We're going to make it sleep for 5 seconds. And then we would print out self.name is full. Okay. And then under that, it will be hungry is false. So to make the lock, we would have the fork. And this is threading.lock. So if they pick up the fork, that means that they're hungry, right? So we would lock the resource. And then otherwise, that means they're full. Then we would make the thread. The first thread is going to be partner 1. That will be the spouse. That's going to be the wife. Partner 2, that's going to be the husband. And so in this one, what you see is the partner 2, even though you instantiate this object for the spouse, the parameter is that you would pass, right, your whatever that you want to name. That's going to be the husband. And then the next parameter is going to be partner 1. And we redefine this by saying partner 1.partner is partner 2. Okay. Because itself is the same, right? So we're saying partner 1.partner is partner 2. So the partner of partner 1 is the husband. We would start the both thread, join the both thread, and then finish. So I run this and I would expect it infinitely going, which it does. So let's stop it so we can see, right? So when you run this, it's gonna never exit this. Okay. Just the wife is waiting, the husband's hungry, the wife is waiting, the husband's hungry. So you would see that, and then it's just infinite. So this is the life lock. Okay. So you don't really have progress, and it's never going to reach the end of the program here. All right. You can step through it too so you can see. So that's an example of life lock. Then in the next part, which is chapter 20, we're going to talk about starvation. And starvation is another issue that we must handle. So starvation is a situation where low priority processes get blocked and high priority processes proceed. That means that the high priority processes takes all the resources, and the low priority processes never get to complete or start sometimes. Okay. So when a process cannot gain access to the resources to continue, your program will not have progress. And so the example here, it shows you that one process is responsible for important instructions and it would start first. Another process is going to handle less important execution. So it's not going to start. It's going to start after the first. And the last process is going to handle non-important, right? It's really simple, frequent tasks. So if all of these three processes are using the same resources, then what you would see is the priority execution is going to take place. And ideally, if it works out, if we resolve it, it's going to be priority execution, then the second process, then the last in order. But because it's using the same, right, none of the process can run because the first process would just take up all the resources. And the third process will never be able to start or finish because the execution would never get there because the first process is hanging up everybody. So the cause of starvation is that one process that required the most priority in the resources dominate the execution flow in the CPU, and the low process thread is not given the opportunity to execute. Or the high priority process or thread use non-shareable resources, preventing the low priority process from executing. Or you have the low priority threads or processes waiting infinitely for the resources because the high priority processes are occupying the resources. So to really sum this up is that the low priority resources will never get to execute because the high priority dominate or use the resources and preventing the low priority from executing or using the resources. To fix starvation, you would resolve it by scheduling technique. And you need to implement queues, and we talked about this before. Queues allows you to store and coordinate how your threads can update, right? Because ultimately it is a container. You set up a data structure where it would append the update, right? Or you can increment the threads that are waiting to access the shared resources. So it allows us to set up a time slot for each of the thread or the process to execute while it's accessing the resources. So starvation ultimately is one process or thread that eats all the resource and the rest would just wait and be hungry and not get to eat at all. Okay. Any question? And starvation is mostly a part, chapter 20. You can find it on page 14 and 15. So in the next part, this is going to be how we would be able to resolve starvation, is scheduling. So here the authors recommended that you need to distribute execution flow and allocate resources equally and appropriately. And we can implement an order in the schedule, but what will happen is the low priority is going to be led to starvation. And so in that case, if you have an ordered scheduling, be careful with your priority because the low priority threads will never get to execute. And this is called the priority inversion. Okay. So here what you see is you have the priority level, low, medium, or high. So the low, it's going to take the flag, which is your lock. And then the high is going to take, so that will be 2 seconds. The high, let's say it takes it for 1 second. And then for the low priority inversion here, what you see is that the low is going to release the lock. Then during that next 1 second, and then the following 1 second, your high priority process or thread would release the lock. Okay. So as we proceed in time, we want to think about how we can coordinate the lock, release, and acquisition or acquire. So here it tells you that the combining the priority inversion and starvation would lead to a situation where high priority tasks are unable to execute the instructions. So you don't want priority inversion or starvation or both. Okay, and the causes, you can find the answer for our prior question on page 15. Hold on while you set, let me put this back here. Any question? And again, this is on page 15. So the book example, they provided an example related to starvation. So a lot of the program that we write for IO, we would have a reader and a writer thread, right? You would have the thread that reads like a document, it reads the data, and then you would use the other thread to write out the data. Okay. So in this example, what you see is the reader thread access the shared resources and read the data. The writer thread access the resource and mutates the content of the context of the file. Now, for the reader and the writer, they cannot access the same resources simultaneously because you want the read to be able to access the resources first in order to read the data, and then the writer. So in this example, what you see is you would have here's your reader 1, right? Access the shared data, reader 2, and then your reader R. And the same thing with the writer. Now, the readers can only read the data that is not performing any updates, because when you write, that means you save the data and that performs an update. So when you read, your data cannot be written. So simultaneously, they cannot be accessing these resources together. So how to resolve this problem is, first, you can impose the lock on the text file and make it non-shareable, where only one thread can use it at one given time. So I can lock it for a specific thread, like I would have reader 1 and lock it for that. And once that's released, I can then give it to the other thread. The second solution is that if you're using multiple readers, let's say that I have a thread pool for readers, we can access that file simultaneously because the file is not altered, because we didn't allow the writer thread to access it. And that means that no reader needs to wait for the updates in order to read. And to implement this, we would use a counter to really sequence the number of readers, or identify, right, coordinate the number of readers and the lock resources. And we would loop through it. So you would then do a decree. So you would subtract 1 for every loop. And so when it reaches 0, then you're going to release the lock. So the first reader is going to acquire the lock for the resource. Then after that, the subsequent reader is going to have to relock until the last reader is finished. And so the process for this is known as reader preference. So we would have multiple readers simultaneously accessing that data. And we would prioritize the readers over the writer, which might not be what we truly want, because sometimes you want to see the update data, right? You want to read the update data instead of just read the data before it updates. Okay. So while this is a feasible solution, it is not a realistic solution, right? For real world. So you can use this program and run, and I'll just go through the code here. So you would have the function called writer, and then you would globalize your text and your word count, or W count. Then you would have a while statement while the counter, remember that what we said, we're going to increase on the word count or the W count. If the W count is 1, we are going to acquire retry, which is the lock. Then we have the statement with a with statement. With resource, we're going to print writing is being done, and then we would implement the thread. So you want to append or write the text or save. Basically, that's what you're doing, is to save. Then your text is going to be incrementing, and that's also another thread. Then now what we're going to do, the counter to subtract so we can release. So as it read more text, right? For more text, right? We want to make sure that once it reaches 0, when we decrease it, we're going to release the lock. So when we acquire the lock, we're going to increment the word count. And when we before we release the lock, we have to decree it until it has 0. And that's how we're going to release. And this is for the writer. Here's the function for the reader. And so we would have an R count as a global variable. We're going to have a while loop, while true. It's going to retry. So our counter is going to increment similar to the last one, right? As it reads. And with that, we're going to lock the resource. Then we're going to print reading is being done, and it shows the current thread. That's for our reader thread, and print the text. Then before we release, just like the writer thread, we are gonna decree the counter and then release. And we would define our text. This is some text. Initialized our W count at 0 and R count at 0 for the loops. And then we'll create the lock. So for your counter, your R counter, so this is for write and this is for read, the resource, and then the retry. As this is a thread pool, so we would create our thread pool, and our target is going to be the reader because we are going to have reader preference and we're going to loop through it. So that will be up to range 3. And then our second thread is going to be for the writer. That will be 2. We would then start the thread. Now for the second solution, what we would do is same, we would have the function pretty much the same. Let me double check something here. Yeah. So we would have the writer, we would have an R counter, we would increment the write count. If the write count is 1, we're going to acquire the lock for the retry. So then for the next part, we would print our thread information, and our text for increment is going to be, this is the current thread name. Okay. Then before we release, we would decree the counter. When it gets to 0, we would then release. Next part's for the reader, very close to the writer. So we would have an R count. If R count is 1, we would acquire the lock. Then print your text. Before we release, we would decree by 1. When it reaches 0, we're going to release. Your text is going to be some text. Then W count we initialize at 0. So your write count and your reader count is at 0. We created the locks. So your W counter, your R counter, your resource, your retry, just like the last example. And then this is going to be our writer or your reader. But in this one, we're going to combine both, right? So in the last one, the reader preference, you only include this part for your thread pool, as it's going to loop through that. So then your writer here is going to be 2. You're going to start the thread. Okay. So in this case, our thread pool is going to be both. So run both of these programs, and then you can do the comparison, and you can see the difference. Where is solution 1 better than solution 2, right? We mentioned that solution 1 it's fine as it's written in code, but realistically, is it practical? So when you implement your solution, you have to think about like the process that you're trying to perform. Is it practical? Is it realistic? Is it what you really want to achieve as far as your goals? Okay. So what you can implement the writer's preference where readers are gonna face starvation. So it's gonna wait until the writer is complete and then it's gonna read. So in this example, it shows that you would have a lock for the writer as the writer is gonna be the preference. And the reader won't be able to execute until that's done. So in starvation, to handle starvation, the thing that we need to focus on is we need to really think about the low priority threads on how we would coordinate the priority in that, right? That means that you need to bring it up in the priority level. And we would set up a queue, first in, first out. So a data structure for our threads. And that way we can set up the request sequence in how it's accessing the resources. And use priority queue to prioritize your thread that is waiting. We can go from the top priority to the least, and eventually it would reach the least priority and execute instead of starve it out, right? You don't want the less priority one to endlessly wait. It will get to the less priority if you set up a queue. Okay, so we talked about using queues, increasing the threads in the priority that's waiting for the resource. Next, we're going to talk about race condition, which is chapter 21. So race condition is when your output is dependent on your scheduling. And so your ordered task is executed based on how you set up the schedule. If your data is mishandled or corrupted in the process, right, you would have a bug in the program, and that can be on hardware or software. So that means that because of the schedule, you might have a different order on how the task is executed, where your data becomes inaccurate. Okay. So to fix race condition, we would use mutual exclusion to prevent data corruption in critical sections. So the important area of your program, you want to dedicate data container specifically for those critical processes or threads. And that will become mutually excluded from the rest of the resources that are shared by other threads. And compare race condition to how this can be a security issue, right? Race condition can occur with authentication, and sometimes that can be an issue, especially for web application or database. So when your data is corrupted, let's say the user input username and password, if it is corrupted at the time of check to the time of use, right, that allows the user to have more access than they should. Okay. Because it's not able to control the resources between the credential and the authorized rules for the authentication. And this would lead to privilege escalation or gaining access. So an attacker, if they would look at the bug problem in the program, let's say that this is implemented for the authentication part, and that's how they can escalate the privilege. Or in some cases, they would purposely do this to the program to escalate the privilege, right? To make a race condition for the authentication script. So that way they can be an administrator versus a regular user, which is more restricted compared to the administrator. Any question? But this is just an area that you can see race condition. It doesn't necessarily be the only area on how race condition happens for security in your applications, right? But this is a common area. Okay. Well, I did not, oops, sorry. Well, I did not put too much over here, but then if you look at the critical sections, it talk about critical sections here. So if your critical sections are modified, like that's your important data, if it's changed, then your threads is going to be, because of scheduling, then your threads are not going to be able to access it appropriately. So that would allow multiple agents to use critical conditions, so other threads won't be able to do that. So this here, so the incorrect behavior, you have to share data. Task 1 is going to read the data, edit the data, then write the data, right? But when it's doing that during the edit, task 2 is actually reading the data and then write the data. So you don't have the appropriate update because the schedule is off. The correct behavior, you would have task 1, right? Ask it share the data, read the data, edit, write, and then task 2 is going to lock that data, read it, edit, and then write, right? This is the right way. This is the wrong way, because if task 1 read, edit, but while edit, task 2 read it, it doesn't have the updated information. And you can see this with, server automated synchronization. That can also happen too, with how if we have a race condition in our script, you're going to have mismatch or non-updated information between servers, or you would have inaccurate data, or in some cases you would then have a potential exfiltration or whatnot through authentication. So look at this example, and then I also included the code for you to see. Okay. So in this one, we're using random threading and time. You have a function for update. We would use a counter. We create a current counter. This is going to be the counter for reading. And then we would have random int for our sleep. Then our counter, we're going to update that by incrementing 1. So updating the shared resources. We initialize counter at 0. As we have current counter is counter, right? And then counter is going to be current counter plus 1. Here's our thread pool. And our target is basically the function, which is update. we would loop for the start and loop for the join. And then we print out the counter and then finished. So for this example compared to the next example, what you would see is that we would then control the process on how it shared the resources. So you're going to see something very similar to the prior one when you look at this, right? Where, let me see, you would have account lock here that's implemented, and that's going to be able to lock our or flag. So you create a threading lock here. So your lock object, and you would use that in this example to prevent your race condition. So locks, we have to identify the critical conditions so that way you can prevent race condition by locking, right? And we would then release it when after that section of your code that's considered your critical condition, we would release the lock. And so locks must be associated with the resources. Otherwise, you allow other threads to gain access to it, right? And so locks is a way that we can flag that resource for the use of that critical condition before it's released. Okay. So we would acquire that lock and we would make it mutually exclusive for that critical condition, and then we release so other threads can have access to it so we don't come into a deadlock. Okay, so make sure that we know what a life lock is, the type, your deadlock, Coffman conditions, what happens with race conditions and how you can prevent it. And then in our lab, we're going to work on GIL and be able to expand on what we've learned so far to apply the concept from today. Any question? Okay, so our assignments is fairly short. If you have the textbook, I encourage you to read it. And or, if you don't have the textbook, use the notes and then look at the programs. I try to copy and paste the code there for you instead of screenshot it. So that way you can run it and compare the differences and look at how you can have, different type of conditions and then be able to improve it with some various solutions there. Okay, so now, any questions? I do have, yeah, so these were, I didn't show you the second example, but I think I put the code there for you. So when you run these programs that are, for the conditions, what you see is that this is the solution for the reader and writer one, right? You would see that it's implemented here. So I do have some printout, and then, it shows that I ran the 20 threads and I finished. So check out your code. Let's take a look at, we'll talk a little bit about the lab. So we'll spend a little bit more on GIL. So touching back, we're going to use CPython a little bit. We'll talk about CPython and how that's used with GIL. And then, in the community, the discussion with GIL. Okay. We've done something like this earlier on, but I'm going to come back to what we've seen before. And now we know a little bit more. So we are going to benchmark our threads. We're going to test the program like this. So the program is a little longer, but I copy and paste the code there for you. So again, I'm just going to run it in Linux and to demo, right? But if you have the appropriate IDE, you can do that too. Then I'm going to show you how you can do that with your HTTP requests with the worker pool. Okay. And then we're going to work with GIL and parallel programming. So you have variation of example. You can choose from these and take a look at how you can implement you know, your design for your Python program for your projects. And I forgot to share my GitHub. So I'll post the page tonight on your module under your project module. So that way you can take a look at your, I think I have like a couple good example from the last class. So you can take a look at those and see. It might be like many files. So I will put the directory into the subfolder. I mean, the files into the subdirectory and then share it on GitHub. Okay, so I have Jarrell, Jimmy. Let me stop recording.